All right, so still working on the chapter on enzymes, bottom of page 3. So let's suppose I got a reaction where substrate turns into a product. Before the substrate becomes product, it has to go through a transition state. I'm going to define the transition state as X. So that means that substrate has to turn into the transition state and then the product. And where I was wrapping things up on Tuesday was in order to get into that transition state, that takes energy. It takes a fair amount of energy to get into that transition state. And we're gonna split this into 2 steps where we're gonna look at the first step and say that our substrate can turn into a transition state. So let's kind of look at that for the moment. So the substrate can turn into the transition state. We can treat that like any other chemical reaction. So for example, we can define an equilibrium constant for that. Where at equilibrium we have a certain amount of transition state, we have a certain amount of substrate. And now that we got a equilibrium constant, we can go back to the beginning of the semester and we can say our standard delta G. Do you remember? Caught you off guard?
Negative.
Yeah.
Negative delta. I mean negative delta G.
No, this is the delta. This is the delta G. Negative.
Oh, RT. Product over there.
KEQ.
Okay. Yeah.
Okay. All right. So it's in there somewhere. Yep. Okay. So we can define a standard free energy change for the reaction between the substrate and the transition state, and that is our activation energy. So I'm going to erase the little circle there, and I'm going to put that symbol in there for the activation energy. So Tuesday when I drew the graph here, so the substrate has a certain amount of free energy. The product has a certain amount of free energy. And the transition state has a certain amount of free energy. I guess I could call it X, but I think sometimes I identified with that symbol here today. I'm saying X. So the difference in energy between substrate and product, that's just our regular delta G. The difference in energy between the substrate and the transition state, that's our activation energy. And the activation energy is the delta G. We can calculate the delta G just like we could calculate any other delta G from RT log KEQ or whatever. Okay, so.
And this matter would still be the same RT as like.
Same RT.
2.18.
Same RT. Yep, same RT. Same old thing. Same calculation as before. Okay, and the one thing to keep in mind, the transition state energy is always the highest. So the substrate, the relationship between the substrate and product can be either way. If the product has less free energy than the substrate, then there's a negative delta G and the reaction is favorable. We could have a reaction where we have substrate and the product might be a higher energy. That would be a positive change in energy. That would be a positive delta G. That would be unfavorable, but it could exist. But the transition state is always high. The transition state always has a high amount of free energy. So it's always going to take a certain amount of activation energy to get up to that point. All right, and one last thing we'll kind of get to is we can do an equation to calculate a rate constant. So the equilibrium constant for the reaction is going to be related to the delta G, the overall delta G. So if S goes to P, if substrate can turn into product and product can turn into substrate, there's a relationship between the delta G and the KEQ. So the equilibrium constant for the reaction is related to the delta G. The rate constant for the reaction. So we've talked before about rate constant. So there's a forward rate constant, little k, and there's a reverse rate constant, little k. So I talked about them before. They're going to be related to the activation energy. So see if you can think for a moment here. So suppose I have two different reactions. And let's say that this is reaction A, this is a reaction B. So here we've got a certain activation energy. Here we've got a larger activation energy. Which one is going to have the faster rate constant? Which one's going to have a higher rate constant? Might be a little tricky to think that through, but think about what what does a higher activation energy mean? Is it going to be easier or harder for that to react? It's going to be harder. If it's got a higher activation energy, if it takes more energy for the reaction to occur, what does that tell you about the rate? Is it going to be faster or slower? It's going to be slower. Okay, so a reaction with a smaller activation energy is going to occur faster. So there's a relationship, there's an equation here. It's an intimidating looking equation. It's on page 4. But almost everything in that equation is a constant. So there isn't that much to it. So there's an equation here. The rate constant is going to equal Boltzmann's constant times the temperature over Planck's constant. All of that times E to the negative activation energy over RT. So we've got this equation here. If I want you to do a calculation with this, I'll give you the equation. I will, of course, give you all of the constants. So really, the only thing that varies there is the activation energy.
Is that like that's an exponent of E, right?
That is just E. So if you've got a calculator, some calculators will allow you to type in E. If you don't, it's 2.7. It's Euler's constant. I don't know if that term rings a bell. So E is the base of natural logs, also called Euler's constant. I think that's how you pronounce his name. And it has a value of 2.7. It's like pi. It's a number that keeps on going, but you can round it to 2.7. So to do a calculation with this, there are two ways you could do it. The first thing to do is calculate that number there. Let's say you came out with 1,300 or something, so negative whatever. You could, if your if your calculator will let you do e to the something, then you just type e to the negative 1,300. If it won't, your calculator should let you to like type in the number 2.7 and then do that to the whatever power. We'll do an example at some point. If you have a question, let me know. So if I know an equilibrium constant, I can calculate a delta G, or if I knew a delta G, I could calculate an equilibrium constant. So what's going on here, the difference in energy between substrate and product, that's dictating your overall equilibrium. What's going on up here with the activation energy, that's going to determine the rate constants. So the activation energy determines how fast the reaction goes. The equilibrium, the equilibrium dictates the delta G. And when an enzyme is present, the enzyme lowers the activation energy. And if we lower the activation energy, the reaction will go faster. So because of the negative sign there, a larger delta G gives you a smaller K. Let's just do an example real quick. So let's see if we can do, kind of just getting started talking about some stuff on page 4. And I got a question for you. So last time somebody gave me their homework without it. Is that yours or is that?
Oh my gosh, yeah, it is mine.
Okay, let me hold it for a minute.
Okay.
So I thought it was you, but there was one other person who I hadn't gotten it from. So actually, I'll just write myself on my Post-it note to add your notes.
Okay.
And then you can just add this.
Thank you.
Yep, you're welcome. And it was all correct. Okay, so I'm on page 4 of the chapter on enzymes, going through stuff here. We'll do a quick recap and then do a calculation. So, consider a reaction where we're just going to say we've got some substrate that turns into product. That's what we would normally show as the reaction. However, the reaction has to go through a transition state before the reaction is completed. So, for purposes here, I'll call the transition state X. And we can draw a reaction diagram. Okay, so we could look at the amount of energy, free energy associated with the molecule. So S has a certain amount of free energy. The transition state has a certain amount of free energy. The product has a certain amount of free energy. Okay. And the transition state is always going to be the higher energy. If the transition state had a low energy, then it would never want to go past the transition state. It would just stay in the transition state. Okay, so we have for our reaction, we're going to have our delta G for the reaction. That's the regular old delta G. The standard delta G would equal, Margaret doesn't work very well, would equal negative RT log n KEQ. And then the delta G, the change in energy between the substrate and the transition state, that is our activation energy. The activation energy is always going to be positive. So the delta G is always going to be positive. We're always going to have to go up to get to the transition state. Okay, and where I was just getting to is we can calculate a rate constant for the reaction from the activation energy. So I'm going to make up some numbers. I have no idea if these are realistic numbers or not, but let's just make up a number. Let's suppose that for our reaction here, let's just suppose that the forward activation energy, by the way, there's a forward activation energy and there's a reverse activation energy. And by the way, you can kind of maybe see how this all sort of fits in here. So F for forward, R for reverse. The way I've drawn the reaction, the products are more favorable than the substrate. And one way you can sort of see that is it's harder for the product to get to the transition state than it is for the substrate to get to the transition state, the way I've drawn it. So the way I've drawn it, it's going to be harder for the product to get to the transition state than the substrate. That means it's more favorable for the substrate to turn into product. See what I'm saying? It's a taller hill to get up going backwards than it is going forward. So, all right, so we've got a fairly imposing looking equation here. Maybe it's not that imposing, but we've got an equation here where we can calculate a rate constant from activation energy. I'm on page 4, just kind of getting started.
There's that for you.
Great. So let's do an example with this equation. So let's just say that we had an activation energy for this reaction. Let's just, for the heck of it, say that it's 60 kilojoules per mole. And let me, I'm probably going to have to look up the values of these constants here. Does any of you have the Canvas site open?
Mm-hmm. You
got it? Okay. So look up the copy of the old exam number 2. See if it's there. Looks like Sola's close. So the exam 2 in unit 2 from last year, I should have the constants on the last page. Yes, okay, so in a moment you're going to tell me what K and KB and H are. So KB, that's Boltzmann's constant. Tell me.
1.38 times 10 to the negative 23 joules K.
Joules per Kelvin?
Yes.
Per Kelvin or times Kelvin? J,
K to the negative
Okay, let me take a look at that. So.
Is that times?
Yeah, joules per Kelvin. Yep, so that'll be joules per Kelvin. Okay. Yep. And then the value for H is
6.63 times 10 to the negative 34 joules per second.
okay. All right. So remember our RT is going to come out as approximately 2.48 kilojoules per mole. So see if you can figure out how to solve this equation given that. The T is going to be 298K. So KB, there you go. H, there you go. T, 298K. RT, 2.48. Let's do this with an activation energy of 60 kilojoules per mole. See if you can solve that. If your calculator will give you the value of E, you can just take that and raise that to that power. If your calculator doesn't automatically give you E, Euler's number is approximately 2.7.
Yeah, this is 2.7.
2.72?
Yeah.
Close enough. Yeah, 2.7, 2.72. And if I on the test, if I decide to have you do a calculation with this, I'll give you the equation. So don't worry about memorizing that equation. Yeah.
I think I missed it. Can you explain what's the delta G?
That's our activation energy. So that's the amount of free energy it takes to get from the substrate to the transition state. So that's the delta G for going from the substrate to the transition state. That's called the activation energy. And for the purposes of this calculation, I said, let's just assume, I just gave you a value of 60 kilojoules per mole.
So you pretty much gave us all the values, it's just about the
Correct. Yep. Well, the one I did, yeah, I've given you all the values except for the one you need to solve it for.
And on the exam, like that.
Yeah.
it would be.
Whenever I give you an equation, I'm pretty much giving you all of the things you need except the one you're solving it for. But yeah, so everything in this equation is a constant except for what you're calculating there in the delta G. But the KB, the Planck's constant, the temperature, R, those are all things that I would give you, and then I would have to give you a delta G. I'm on page 4, looking at this equation that's in the middle of page 4 for calculating a rate constant. So let me know when you're ready for me to say something to you. Okay, so we've got a reaction, a hypothetical reaction where substrate turns into product. The way I've drawn it on the diagram here, it's a favorable reaction where the product has less free energy than the substrate. So the delta G for the reaction, as I've drawn it, is negative. To get from substrate to product, we have to go through a transition state. The transition state is always going to be a high energy state. Okay, that's just the way it is. So the transition state's always going to be a higher energy. We can define a change in free energy from the substrate to the transition state. So just like there's a delta G from the substrate to the product, that tells us about the equilibrium of the reaction. There's a delta G from the substrate to the transition state. That is referred to as the activation energy with that symbol there. So if we've got the amount of energy it takes to get to the transition state, that's called our activation energy. Where that word comes from is that in order to activate the reaction, in order to get the substrate to turn into the product, we have to activate it. We have to get it to the transition state. And that is going to dictate how fast the reaction goes. The amount of activation energy determines how fast the reaction goes, which we can see in the rate constant. So that's a little k. So the lowercase k is the rate constant. So there's an equation on page 4. I said you don't have to, if I want you to use that equation, I'll give you the equation. It's a bunch of constants, I'll give you the constants. It's a little bit of an imposing looking equation, but if I give you, or if you calculate a value for activation energy, you can then calculate the rate constant. So we were just going through an example. Part of the equation is you have to take E, Euler, I think you pronounce it Euler's number. It's the base of natural logarithms. You have to take E and raise it to a power. Some calculators have a key that just is for E. So some calculators, I don't remember, my phone is being used for the camera right now, so I don't know, but some calculators will let you just type in E. If you're not sure, if your calculator doesn't do that, we can round the value of E to 2.7. It's like 2.718. It's a number like pi that just goes on forever, but you can round. So I'm walking through the equation. This term here at a given temperature is all constants. So KB is something called Boltzmann's constant. And I'll give you the number. Here it is. H is Planck's constant. They all have stuff to do with the amount of energy and stuff that a molecule has. So you've got Boltzmann's constant, Planck's constant times temperature. That's all going to work out to, when you multiply that all out, you should get 5.84 I think there are times I just rounded it to 6, but you're gonna get 5.84 times 10 to the 12th. If I think I did my math correctly. Has anybody else gone through those calculations?
I think I accidentally did RT instead of just T itself.
Okay. So when you multiply out 1.3 times 10 to the negative 23rd, temperature is 298, divide that by 6.63, you should get something around 5.84 times 10 to the 12th, depending on how you round. Do you still have that old exam accessible easily enough?
Yeah.
Let me look at that last page again real quick. Oh, that's the notes. Okay, right, so I made a mistake when I wrote this up here, so it's not joules per second. This is joules times seconds. All right, so when you go through multiplying Boltzmann's constant times temperature, standard temperature, divided by Planck's constant, you should end up with 5.84, depending on how you round, something like that, times 10 to the 12th. If I give you the value of activation energy of 60 kilojoules per mole, when you divide that by RT, so RT is going to be 2.48 kilojoules per mole. By the way, for one thing, the kilojoules per mole just cancel out, so the units cancel out. But 60 divided by 2.48, I get 24, and it's negative. So we're negative, so we got to take e to the negative 24. And on my calculator, when I did e to the negative 24, I came out with 3.8 times 10 to the negative 11. I don't know if anybody's got a calculator that backs that up, or are you able to do that calculation? So e to the negative 24. And again, if your calculator doesn't automatically give you e, you can take 2.7 and raise it to the negative 24th power.
Yeah, 3.71.
Okay, so depending on how you're, and to the 10 to the negative 11?
Yeah.
Okay, so yeah, so depending on how you round e or whatever, you'll hopefully get something in that neighborhood. And then we just got to multiply those numbers together. So that times, you get 4.4? That might be, did you put in that, or did you put in?
Put in 2.7.
Actually, so that's probably.
I think there's E there, but I don't know how to get that.
Does your calculator, if I say inverse, does that mean anything to you?
It does, I don't know how to.
Don't know how to do that. Yeah, so that's just coming out of the rounding error from,
Okay.
on my calculator, it'll actually pull up E, 2.7, whatever, blah, blah, blah. But 3.8 is close enough to 4 that that's just from the rounding error.
Okay.
4 E to the 12. Finally, I come up with 2.2 times 10 to the second. Or something close to that.
Yeah, that's 6.
And 10 to the second, that would end up being 220. And for this term here, with the units, we got joules per Kelvin, joules times seconds, and the joules are going to cancel out, the kelvins are going to cancel out, and our units are per second. Our units are whatever per second. I'm gonna make you do the calculation one more time. You're not gonna have to do all of it, but this is always, that first term is always gonna be this. So at standard temperature, if the temperature is always 298, and I'm not gonna change the temperature on you, but if the temperature stays 298, then this term stays the same. But what would happen if we added an enzyme, and the enzyme lowers the activation energy? So let's say we lower the activation energy from 60 kilojoules per mole. Let's say the enzyme cuts that to 1/3. Let's say we cut it to 20 kilojoules per mole. Redo the calculation. All you gotta redo is that part of it.
It's 6.2 or does G equal?
That's, forgive my handwriting, that's me writing delta G. So delta, the activation energy, let's say now that it equals 20 kilojoules per mole. So slowly we went through, finished the one calculation, and we should get, depending on how you round it or what you put in for E, you should get something around 2.2 times 10 to the negative 2.
For the equation, what does E stand for?
E is the base of natural logarithms, also known as Euler's number.
Oh,
It's one of these numbers, sort of like pi or whatever, that has some kind of meaning that I wouldn't really be able to explain to you. But it's approximately 2.7.
okay. So why is it 3.8?
Well, e to the, you take e to the power of that.
Oh, I did not write that.
Sorry, yeah, okay.
Okay.
So when my delta G was 60, 60 divided by RT with a negative sign comes out to negative 24. So where I am now is, let's hypothetically say that we add an enzyme that lowers the activation energy from 60 kilojoules per mole to 20 kilojoules per mole. Let's redo the calculation. We only have to redo this part here. The other part will stay the same. That part's not changing. So 20 divided by RT is approximately 8.06. If you want to round to 8 would be fine. And it's negative, so it's going to be negative 8. So now you've got to figure out how on your calculator to take e to the negative 8th power. So again, my calculator will let me get e. So my calculator will let me get 2.718281, whatever. If your calculator, if you don't, yeah. That's what you got for your final answer for the first part?
No, just for E.
Oh, just for, E, that is not E. So, E to the negative 8, yeah, so let me, I haven't done, let me see. So E is gonna be about 2.7. Yeah, and then if I go y to the x, if I take, and then hit 8 negative, 3 times 1, 2, 3 to 10 negative, or yeah, 335 times 10 to the negative 6. You're correct. Okay, so now, instead of 3.8 times 10 to the negative 11, e to the negative 8th is going to be, I've got 3.36 times 10 to the negative 4th. Now multiply that by 5.84. 5.84 times 10 to the 12th. Okay, 3.36 -4 times 5.84 to 12 equals 1.962 times 10 to the ninth, 2 times 10 to the ninth. Per second.
Okay.
So what can we gather from this? What can we get? So when I made up the number and said the activation was 60 kilojoules per mole, our forward rate constant comes out to 2 times 10 to the second, or approximately 200, 220. So I'm just going to write, so 2.2 times 10 to the second per second. Now, if we reduce the activation energy to 1/3, so we cut it by 2/3, this goes up by the power of 7. That's like more than 1 million. That's what? The 7th power is 10 million. That made the reaction, that made the forward rate constant 10 million times faster. So it doesn't take much lowering the activation energy to get a big increase in the rate of the reaction. So basically by lowering that hump, it doesn't take a lot to get a big change in the rate constant. So it goes much faster. So that's what an enzyme is doing. I'm going to draw something on the board. This is not in the notes. You can ignore this. Boltzmann must have been a pretty darn smart person, I guess, or whatever. You know. So, but there's a thing called a. You can ignore what I'm saying as far as tests go or whatever, but there's something called a Maxwell-Boltzmann distribution. Where at a given temperature, we can get a distribution of, in a population of molecules, how many of them have a certain amount of energy. So we're going to have energy on the x-axis, and then we're going to have the number of molecules with a certain amount of energy. So just, don't stress out about this, just kind of maybe see if this helps you through. So imagine we had 1 million molecules. So imagine I've got 1 million substrate molecules in a beaker. They're not, even if they're all in the same beaker at the same temperature, they don't all have the same amount of energy. As they randomly bump into each other and whatever, they're not all going to have the same amount of energy. And Boltzmann and Maxwell, I guess, apparently figured out you're going to get a curve that looks something like this. And most of them are going to be pretty similar. So if you've got a population of identical molecules, most of them are going to have a fairly similar amount of energy. But there's going to be the outliers. There are going to be some that don't have much, and there are going to be some that have a higher amount of energy. So this would be the amount of energy associated with your basic substrate molecules. In order for somebody to get to the transition state, they're going to have a very high amount of energy. So what Maxwell and Boltzmann figure out, or whatever, what this tells us is that at any given time, there aren't going to be many substrate molecules that have that much energy. So there aren't going to be many that have enough energy to reach the transition state. So what can we do to get more substrate molecules to be able to turn into product faster? One thing we could do is raise the temperature. So by the way, so one thing we do, what happens to the amount of energy if you raise the temperature? If you raise the temperature, you get more energy. So if I raised the temperature, I would get a curve that shifts it up more like that, so I would have more molecules with more energy if I raise the temperature. Or what we can do, instead of making them have more energy, we can lower the activation energy. So when the activation energy is here, only these molecules have enough energy to go through the reaction. If we lower the activation energy, then more molecules are able to reach that level and will be able to become substrate. Or sorry, will be able to become product. Anyways. And last thing about all this stuff. There's a forward activation energy. There's a reverse activation energy. So if we look at the reaction backwards, what would it take to turn product into transition state? There would be an activation energy for that. And it would follow the same rules that I just went over. It would follow the same rules. Okay, so the way I drew the reaction, it takes more energy to get from product to transition state than it does from substrate to transition state. So there's going to be a faster rate constant going forward than going back, and that's why at equilibrium we end up with more product than substrate. It's harder for the product to turn back into the substrate than it is for the substrate to turn into the product. The product has to go up a higher hill than the substrate does. So when the products have less energy than the substrates, that's favorable because it's going to be harder for the product to turn into substrate than vice versa. Okay, so that just puts some numbers to how an enzyme makes a reaction go faster. And because of the exponential nature of that equation, a small change in the activation energy gives us a big change in the rate constant. All right, so now we're going to get to the main part of the whole enzyme thing. So, are some of you are pharmacy? Pharmacy? Okay, you vet med. That's right. I knew that. Okay.
Physician assistant.
PA. Okay. So, do you have any idea if you don't know what you're doing?
As well.
I'm sorry.
Vet med as well.
Vet. Oh, okay. All right. So pretty much everybody in this class is going into pharmacy or medicine of some sort, something like that. Well, there's a whole lot of pharmacy, there's a whole lot of medicine that relates to enzymes. So, have you ever heard of beta blockers?
Yes.
Well, actually, beta blockers was not a good example, sorry. Beta blockers are not blocking an enzyme, they're blocking a receptor. ACE inhibitors. There's a category of medicine, they're used for similar things. ACE inhibitors, beta blockers, both generally used to lower blood pressure. But like ACE inhibitors, there are various medicines, pharmaceuticals, medicines that do their thing by acting on an enzyme. Okay, so as people develop these drugs or investigate these drugs or try to deal with these things, the people in the pharmaceutical companies or whatever who are doing this stuff have to understand how the enzyme is working and how the drug is affecting the enzyme. So we're going to talk about something called enzyme kinetics. And enzyme kinetics is basically asking, what's the job of an enzyme? The job of an enzyme is to make a reaction go faster. Kinetics is speed, So this is just a study of how fast the enzyme is working. How is the enzyme working? I'm going to use the term V quite a bit. V is going to mean velocity. In other words, the rate of the reaction. How fast is the reaction going? How fast is the enzyme turning substrate into product? Okay, so we're going to start off with the simplest possible enzymatic reaction. We're going to have an enzyme, and we're going to have just a single substrate, and that single substrate is going to get turned into a single product. Okay, so the simplest chemical reaction you could have is A turns into B, or in our different language here, substrate turns into product. Okay, so that's the simplest reaction we could have. We're not going to get any more complicated than that. But we got to bring the enzyme into it. So the enzyme has to bind to the substrate. That forms something called an enzyme substrate complex. From that enzyme substrate complex, when the enzyme substrate complex forms, one of two things can happen. The enzyme could let go of it without doing anything. So the enzyme substrate complex could just go back to enzyme and substrate. That's why I drew the reverse arrow. Or it can turn into product. And then we're left with enzyme and product. Okay, so back 100 and something years ago, a couple of researchers, Michaelis and Menton, I think they were working in Germany or something somewhere, in Europe somewhere, worked out a mathematical analysis of all of this that allowed us to look at how fast a reaction is going in relation to the amount of substrate we have. So if I give an enzyme a certain amount of substrate, how fast will it go? Okay, so if we give an enzyme substrate, how fast is it going to be? And then from there you can figure out what different things affect the enzyme, make it go faster, make it go slower, etc. So couple things here. So what is our velocity? So the velocity is the amount of product we get per time. So velocity equals the change in the amount of product per change in time. So from our perspective, if we give an enzyme substrate, what's its job? To make product. So I think sometimes of like a factory or something like that. If you have a factory that takes metal and makes it into, what do you turn metal into? Shovels or something or whatever. You have a factory, you have workers, you give them metal and they're supposed to make shovels for you or something or whatever. Well, how good are your workers doing? Well, how many shovels do you make every day? Or if you're, whatever factory you've got, how many products are you turning out every day? So the amount of product per time, that could be something like moles per second or moles per minute or something or whatever. You're making a certain amount of product per time. And if we, taking the enzyme out of the equation for a minute, if we have substrate goes to product, going back to something from the beginning of the semester, the velocity is going to simply equal our rate constant K times the concentration of substrate. Okay, so now, can you see if you guys can remember this real quick? See if you can remember. If I have a reaction A plus B goes to C plus D, and I have a forward rate constant and a reverse rate constant, what would be my equation for the forward velocity? Kf times the concentration of A and times the concentration of B. So the forward velocity would depend on both. Why does my equation over here depend only on substrate and not on enzyme? That's because we're going to say that the concentration of enzyme remains constant. Okay, so our substrate is getting turned into product, but you might remember our enzyme doesn't get turned into something else. So because the amount of enzyme is going to be a constant, we can drop it from the equation. Okay. So what's going to happen if we mix enzyme and substrate into a beaker? So I've got a drawing on page 5, and I'll try to kind of go over it with you here. So we're going to start with a certain amount of substrate. We're going to start with a certain amount of enzyme. And you'll just have to take my word for this. So it's typical we're going to have a lot more substrate than enzyme. Okay, so we're going to have a lot more substrate molecules than enzyme molecules. What happens when we put them together is enzyme molecules are going to bump into substrate molecules and form enzyme substrate complex molecules. If I've got a lot more substrate than enzyme, I can turn all of, or almost all of my enzyme into enzyme substrate. So imagine I have 10 enzyme molecules and I have 200 substrate molecules. When I put them together, fairly quickly I should get most all of those 10 enzyme molecules should meet up with a substrate. So the amount of free enzyme is going to go down, and I'm going to see the formation of enzyme substrate complex. What's going to start to happen to this?
Goes down.
That number is going to start going down, and what's going to start to appear? I've already got the ES complex. What's going to appear next? I'm going to start to get product. Okay, so as ES, as enzyme substrate complex starts to form, I should see a drop in the substrate concentration, and I should see an increase in the amount of product. And if the reaction goes on long enough, at some time the enzyme and the substrate and product should reach whatever equilibrium. I don't know if I didn't draw my diagram out that far, but the amount of product goes up, the amount of substrate goes down. If it's a favorable reaction, I would end up with more product than substrate. And the enzyme substrate complex is going to remain fairly constant until the substrate concentration drops to a certain point. At some point, as I'm losing substrate, the amount of enzyme substrate complex will drop. So I think y'all are familiar digging your head somewhere. If I've got a line, the slope of that line is the rate. So the amount of something over time. So the slope, that slope is my velocity. That's the change in the amount of product over time. So that's what I want to measure. I want to measure how fast is my enzyme making product. So these people, Michaelis and Menton, one little thing that stands out to me, when you go back to science 100 years ago, 150 years ago, 200 years ago, who always gets all the credit, even not that far ago? It's all men. It's all men. You've probably all heard the story about, people always talk about, people always skip, yeah, it's always, why can't I think of the other names right now? It's always Watson and Crick. And until recently, people always left out Rosalind Franklin. So in this case,
They say Einstein's wife made most of his discoveries.
I don't know,
That's a conspiracy, but-
Maybe, who knows, I don't know enough to pass judgment on that. So this one, so Michaelis and Menton, this is one of the very few things that I teach in any of my science classes that come up where Menton was a woman. So Maud Menton, and she actually got credit for it. Go figure. So, by the way, I read some. Are y'all familiar with the Henrietta Lacks story? Okay, so I'm gonna. A few years ago, I had a small class, and I got everybody a copy. I'm gonna get you all a copy of a book. It's an interesting story that. There's a movie. If I give you the book, read the book before you see the movie. The book's always better than the movie.
What's the name of the book?
The Immortal Life of Henrietta Lacks. Immortal Life of Henrietta. I think it's Lacks.
Yeah, I watched it.
Did you watch the movie once? Yeah, it's a really interesting story. One of the things that makes it even more interesting is it all happened in Baltimore.
Yeah.
So it's all local, yes. So when I was a graduate student, and even when I started doing research in college, all the time you would see research papers, the effect of such and such or something such on HeLa cells. So if you dig into research, scientific, biological, cellular research, all the time you come across HeLa cells. HeLa, Henrietta Lacks. So for years, nobody even knew who she was. Okay, so I'm getting off track, but I'll be quick and I'll get you all the book. But African American woman living in Baltimore, 40s or 50s. So, and she starts to experience pain in her gynecological area, has pain going on down here. Ends up at Johns Hopkins. Johns Hopkins Hospital would do a fair amount of medical stuff for poor people. So for people who couldn't afford to go to a regular doctor. So people in the Baltimore area, they could go to Hopkins and get treatment. So Henrietta Lacks goes. Long story short, at some point somebody diagnoses her with cervical cancer. Okay, so she's got cervical cancer. One of the treatments at the time, or the main treatment at the time, was to take a test tube of radioactive material. I forget which radioactive chemical it was, but you would actually insert it into the cervix and leave it there for some period of time. The radioactivity, so you may be, it's like it's not that different from radiation treatment today. Radiation kills cells, but it kills cells that are dividing faster than other cells. So the idea behind chemotherapy or radiation therapy is you're going to kill regular good cells, but the idea is you're hoping to kill more of the tumor cells. Well, no surprise, it didn't really work that well. But and one other aside, so back in the day, the doctors would walk around with vials of the radioactive stuff in their pockets. A bunch of doctors ended up with like testicular cancer and other cancers because they're walking around with radioactive stuff in their pockets. Anyways, there's one of the doctors at Hopkins was working on a project, so scientists all over the world, scientists in various places, wanted cells that they could just keep growing over and over again instead of always having to get fresh tissue samples. So scientists who were working on cells and trying to figure out how cells work, like, boy, if we just had an endless supply of cells, we wouldn't have to keep getting tissue samples. So different scientists were trying to find ways to collect tissue and get the cells to just keep dividing and keep a continuous supply of cells. So they would take cells from a liver, they would take cells from this and that, they would take cells from something, and they would put them in a petri dish and give them different chemicals and stuff, and they would multiply for a while and then they would die. So Henrietta Lacks, when she was getting treatment for her cervical cancer, people took samples of her tissue, people took samples of the tumor, put them, and one of her samples of cells, they kept growing, kept dividing. And so somebody had it was the right cells, they had the right mix of stuff, and they could just keep on growing these cells from Henrietta Lacks.
Were they like stem cells?
They were tumor cells. So remember by definition, a tumor is cells that just keep dividing. So I'm thinking about this on the fly. So I don't think they would be considered stem cells, because a stem cell gives you different types of cells. The definition of a stem cell is it could give you, like in your bone marrow, you've got stem cells that can give you neutrophils, eosinophils, basically can give you different cells. So these weren't giving different cells, so I don't think they would call them stem cells, but they were just dividing and giving you more of the same tumor cells over and over again. By definition, they're not normal cells. They're tumor cells, but they're human. They're an endless supply of human cells, and I guess you could still learn a fair amount about what human cells do. So, you always think about things in the time. Like, from what I've read, reading the book, I don't think anybody was doing anything intentionally nefarious. So they were despite the fact that she was a black woman in the 50s or whatever, they were treating her the way they would try to treat somebody. The doctor who made the discovery, he gave away samples. Like he did not profit off of it to any noticeable degree. He was just excited about how I've got cells that will keep on dividing, and he was giving them away. Over the years, certain companies started taking the cells and selling them and profiting off of them. I don't know Merck, or I don't remember company names or whatever, but various companies started growing them and selling them and making money. Henrietta Lacks had no idea that people were doing this stuff with her tissue. It was normal at the time, it was fairly normal at the time, probably not only for poor people, but for anybody, when a surgeon did a surgery and took out tissue, for them to do stuff with the tissue. So again, not saying right or wrong or whatever, but that's just the way it was. So the guy at Hopkins, I guess, somewhere as he was taking different tissue samples, he would use, I guess he just got into the pattern of using the first two letters of the first name and the first two letters of the last name. So he identified the cells as HeLa. So somehow those cells were identified as HeLa and just started distributing. So Henrietta Lacks knew nothing about them. At some point in time, I don't know when, I don't know if this was 30 years ago or 20 years ago, somebody got the idea, well, where did they come from? So where did these cells come from? And went back to Hopkins, I guess, or whatever, and dug into things and did some research and was able to come up with Henrietta Lacks. By the time this was figured out, she was long dead. So she died, not too long after this, she died of the cervical cancer. Somebody contacts her children. She had something like 4 or 5, 6 children, and somebody notifies their children hey, did you know that, and then I won't say too much more about that, but this is where the book gets really interesting. So one thing that comes up is they learn that people have been making lots of money over the past 50 years or whatever from her tissue sample. And then it's interesting, like her descendants, you know, fairly poor people growing up in Baltimore, they don't understand the biology. They don't understand, and they're really freaked out by the idea that their mother's cells are still alive. And at some point, I think somebody asked the question, like, is our mother in pain? Like, and as a biologist, I'm like, but to somebody who doesn't, you just hear that, like, part of your mother's body is being kept alive, shipped around the world, having experiments done on it, and like, whoa, what? And so it's, anyways, I didn't take time to read the full article yet, but something passed through my feed or something about a settlement between her family and one of the companies. So something might be going on where they're getting some compensation for that.
That's good.
Yeah, and I think for a while now, I think like if you're having a surgery done, I think one of the things you sign sometimes, they're like gonna ask you to sign, like if we take tissue, can we do what we want with that tissue? And I guess you have the option now of saying no. Anyways, so interesting story. I forget how I got into it. Yeah, HeLa cells and enzyme kinetics, whatever. So we're about out of time. So let me just wrap up again for a second here. So, and I guess I got into that somehow talking about the women in science. Mm-hmm. So Henrietta Lacks was not a willing participant in it, but enzyme kinetics. Leonore Michaelis and Maud Menton, one of the rare women from years ago acknowledged for her role. So what they're going to do again, what I'll get to next time, so if you put an enzyme and a substrate together, if you can measure the formation of product, when I was a graduate student, the stuff I did in grad school for my PhD, a part of that was looking at enzymes and measuring the rate of enzyme. So you could put enzyme and substrate in a tube. There are different ways you can measure the product as the product forms. And then you can calculate the rate and get your velocity. And we can do that experiment at different substrate concentrations under different conditions and see how it affects the velocity. So we'll get into how Michaelis and Menton gave us the analysis to know what we're doing with that. So that'll be next time. So you guys may have noticed already, so a couple of people have given me the homework assignment that was due today already. And I I said I'm going to make it due next week, after spring break. So you don't need to get, now yours is all correct.
Can you keep it?
So yes, so since you got it all correct, I was going to say I may as well keep it. I don't need to give it back to you. You've already submitted yours. I think I went back to you. Yours was all correct, except remember to put units on it. So you have until after spring break to get that homework assignment to me. I don't have any big plans for spring break. Get work done, do stuff, whatever. If between now and the time you get back, if you have a fairly concise question about something, you can email. I'll get back to you at some point. I'm posting an announcement today. I'm delaying your exam by a week as well because I'm behind, which. Yeah, so whatever, I'm going to teach you stuff, you're going to learn good stuff here, whatever. So anyways, yeah, so enjoy your spring break. Looks like latest weather forecasts I've been looking at show that we might actually have some decent weather. And I will make a note that you're the one who gave me that assignment without the name on it, so I'll enter the
Sorry
points for
about
you.
that.
That's okay, no worries.
I guess I was stressed out, I don't know what happened.
It's just a good thing I don't have a class with 200 people in it.
Right?
So-
You would have been like, hey, I don't care who
Where
you
does this
are.
come, yeah. So.